right, ladies and gents, it's time for another riveting lesson in factoring. Again, everything that we're doing so far this week, it should be just a review for you, so hopefully you're remembering it as we go along. All right, so we're going to look at the special factoring pattern of difference of squares. And difference of squares is a factoring pattern that we look for if we have two terms, and exactly two terms. But before we jump into the factoring, let's review some of our perfect squares. So, yep, that's right. I'm just going to sit here and list out 2 squared, 3 squared, 4 squared, and I'm going to keep going and going and going. Well, I eventually will stop. So we got 36, 7 squared is 49, 8 squared, 64, 9 squared, 81, 10 squared, 100, 11 squared, 121, 12 squared, 144, 13 squared, and we'll stop there. Because anything else you should be able to, something stuck underneath this paper. Anything of these else you should be able to look up and use Desmos, type into Google what's the square root of, and you will be able to determine whether or not you have a perfect square. But these numbers should be familiar to you. So when you see numbers, these guys right here, recognize that they are perfect squares, which means we can take the square root of those numbers, and that's going to be kind of an important task for us to do. So we'll pick on this 64. If I take the square root of 64, what you're really asking is, what number squared is going to give you 64? And that answer, of course, would be 8. So the square root of 64 is equal to 8. Now, not only should we recognize some numbers, you do need to recognize some things in terms of variables. So if I take x to the first power and square it, lo and behold, I get x squared. If I take x to the second power and square it, power to a power, rules of exponents say I multiply those exponents. X cubed and square it, that gets me x to the 6th. X to the 4th squared gives me x to the 8th. And all of these terms are also perfect squares. Perfect squares that are variables are very easy to identify because of the fact that all of the exponents are even. So kind of a little cool thing that goes on with those. So anytime we are recognizing, if I want to determine whether or not I have a perfect square in terms of a variable, look at the exponent. If the exponent is even, you have a perfect square. So what we should also be able to do, let's pick this guy, is we should be able to take the square root of a variable to a power. And easy enough to do. If I'm taking a square root, that little index right there, a square root, you don't write it, but you do assume it to be there. Just means I'm going to take this little guy right here and I'm going to divide that exponent in half. So we can say that the square root of x to the 6th is x cubed. And that's verified because what did I square to get x to the 6th? I squared in x to the 3rd power. All right, so knowing some basic background things of what you're looking for is I'm looking for a difference. A difference means to subtract. Oops, my pen is knocking the camera. And of course, squares. We're talking about perfect squares. And we just reviewed a whole bunch of perfect squares. So a difference of two perfect squares, since this is two terms, is of the form a squared minus b squared. So if you're being asked to factor something and there are exactly two terms, look to see if the two terms are a difference of squares. Meaning that the first term is a perfect square, the second term is a perfect square, and you're subtracting those two terms. Difference of perfect squares. If you do have two perfect squares, you're going to take the square root of the first term and the square root of the second term. Notice I ignored the minus sign because I'm taking the square root of both of these positive terms. We already know how to do this one. Half of 2 is a. Half of b squared is b. And it will always factor into this pattern. a plus b, a minus b. Just to verify that, let's use a quick little box method just to verify, does a minus b times a plus b really give us a squared minus b squared? Well, row to column is a squared, that's ab, that's negative ab, that's negative b squared. Those terms cancel out, and lo and behold, you are left with a squared minus b squared. Now, this whole pattern, too, this difference of squares, there is a special name for these two factors that you have here. These factors, when you factor a difference of squares, are called conjugates. And we're going to use the idea of conjugates throughout the remainder of this course. So when you factor a difference of squares, you're going to be factoring into what's called a pair of conjugates. So let's do a couple of examples. Now, the very first lesson you had in factoring was GCF. Before you proceed with any other factoring, you should stop and take a look and ask yourself, is there a greatest common factor? Especially if numbers look large, chances are there is a common factor. If you factor it out, it's going to make life easier. No common factor, I can't divide anything to both 9 and 25 other than 1. But you should recognize 9 as a perfect square. That's 3 squared. 25 is a perfect squared, because that's 5 squared. And x to the second, since it has an even power, is also a perfect square. I'm subtracting the two terms. This is a difference of two squares. So now, to factor it's easy. We just need to take this term right here. This is a squared. This is b squared. And we're going to find the square roots of those terms. So we take the square root of both the number and the coefficient. Square root of 9 is 3. Square root of x squared is x. Again, we take the exponent and divide it in half. Square root of 25 is positive 5. So this value right here is a, this is b. And you're 2 steps away from being done. So we're going to take those terms, 3x plus 5, 3x minus 5. This and this are equivalent. Multiply this out together, you're going to get 9x squared minus 25. So 3x plus 5 and 3x minus 5 are the factors of 9x squared minus 25. It's not a difficult task, it's just making sure that you remember how to do it. All right, next example. Feel free to pause if you want and try it on your own. 121, well, that's in my list, that's 11 squared. 16 is 4 squared, and x to the second is even. So yes, I definitely have two perfect squares. I'm subtracting the two. I'm ready to move on. Your first term, square root of 121 is equal to 11. Because it's the first term, it has to be a. And yes, order does matter. B will be the result of 16x squared, and the square root of that. Square root of 16 is 4, square root of x squared is x. And this is b. So a minus b, a plus b. I don't care if you do the minus first or the plus first. What I do care about and what is important and makes a difference is whether or not you put the square root of this term first versus this one. So they have to go in the correct order. All right, just a couple more, and then you should be good to practice. All right, in number 3, I hope you all recognize that 2 is not a perfect square. I have my little star beside it because, true, 2 is not a perfect square. 8's not a perfect square. Neither one of those numbers is on my list of perfect squares. But you should recognize that both 2 and 8 are divisible by 2. So I could take out a greatest common factor. 8 divided by, this is 4. Now, just because you factored doesn't mean you are done factoring. Our goal is always to factor completely, which means once you've done one type of factoring, look to see if you can do any more. So I take a look at what's inside the parentheses and ask myself, can we go any further with this? Well, I recognize x squared is a perfect square, 4 is a perfect square, and we're subtracting. This is a difference of squares. So I'm going to do my square root, here's A, here's B. Your GCF, tried to say greatest common factor and GCF at the same time, it didn't work, has to be a part of your answer because you want your answer to be equal to the original problem. So GCF, A minus B, A plus B. So if you handed 2 times x minus 2 times x plus 2 to someone, they should be able to multiply it and get this answer. Okay? And don't get weirded out if you see multiple variables. Again, as long as it fits our pattern, we're good to go and we can apply our factoring rule, the conjugates. 9x squared, both perfect squares. 16y squared, both perfect squares. Subtraction checks all the boxes. This is a difference of squares. So I'm going to take my square roots. That gets me 3x. Square root of 16y squared. That's 14y. Here's your A. Here's your B. So 9x squared minus 16y squared is 3x plus 4y, 3x minus 4y. Again, this multiplies out to give you this. All right, one last one, and I'm hoping you all look at this and go, hey, wait a minute, something's kind of off about that one. And you would be correct. 144, perfect square. 81 squared, perfect square. Plus? Nope. There is no formula for the sum of 2 squares. We cannot factor a sum of 2 squares. So you could say that this problem is not factorable, but that also would mean that nothing will divide evenly into 144 and 81x squared. So we often will also say then, this polynomial is prime, which means it's not factorable, and the only thing divisible into this is 1. All right, you've got some problems to practice. Good luck.